So, good day to everyone. Welcome to session 7, Process Understanding. Process Understanding is such a wide notion that it fits all the talks in this session. I'll be your host. My name is Johannes, and I will gladly hand over to our first speakers, Johannes Viehhauser and Maria Doerr. Please, when you're ready, you can start with your presentation.
Thank you. Johannes, are you able to share your screen?
It seems that Johannes is frozen, at least in my screen.
Okay, no worries there. We're quite spontaneous, so then I will share my screen so that we can go ahead despite the technical difficulties, I think.
That's very good. I think redundancy is a fantastic notion.
Okay, let's see if I can share my screen. You should be able to see it now.
It's coming. Yeah,
go into
we see it.
mode.
We see it in this. Yeah, we see it in presentation mode. So
Perfect.
Go ahead whenever you're ready. Yeah,
that's lovely. So I will go ahead and start. Welcome, hello to our presentation on RPA, Robotic Process Automation. The title of our research is Digging for Gold in RPA Projects, a quantifiable method to identify and prioritize suitable RPA process candidates. We'll go into detail about that during our presentation, of course. I would first like to introduce my research partner and myself, Johannes Viehhauser, who's I think still working on joining the meeting at this time due to some technical difficulties, but he will be there in a second. And myself, Maria Doerr. We're both researchers from Technical University of Munich in Germany, and we've been working on this project in regard to RPA over the past months and a year now at the chair of management accounting at Technical University of Munich. Maybe shortly for those that don't really know what RPA is, Robotic Process Automation, it's a software technology that can be used to automate all sorts of processes that are mostly digital. So you could also call these sort of robots digital workers, so to say. First, I would like to give you a short overview over the research that we have been working on. So why did we actually choose this topic? That's very important because we noted from research and literature and also talking to experts that actually these RPA projects tend to fail a lot of times because the process selection was not good. So processes were actually chosen that were in the end unsuitable, and that resulted in failure. It's also economic problems there, and then the success of such automation initiatives in general. So what did we do? We came up with a model that's really systematic and generalizable so that we were able to actually prioritize certain process candidates, and then in the end be able to say which ones are really suitable for RPA and which ones aren't. And we did that by using some weights for those criteria. We will go, of course, into detail about that in a second. How did we do that? We used design science research. We came up with weights to actually quantify our model. Of course, we took into account really in-depth literature review, expert interviews. We also conducted a survey to really gather enough data here so that we could actually come up with a good quantifiable model. And in the end, what does that mean? Well, our research could actually confirm some findings that we had found in previous research. We also found out that a high degree of standardization of that process that you are choosing to be automated is one of the most important criteria actually for process selection in RPA. So that really goes in line with existing research, but also adds a lot of new components on top of that. Now I already jumped into the motivation, which is the first part of what we will be speaking about today. Second, I would like to present to you our research approach. So what did we actually do? How do we collect our data and so on? And then my colleague Johannes will actually present the model to you in detail in the third part of this presentation. So I will skip on to talk about the methodology here briefly. So I already mentioned we are using science research. So that means we actually iterate through our model to improve it. And we started there with an objective-centered approach, which actually means what do we want to achieve? We choose the objective first and then work towards that goal. So what did we do first? I already mentioned data collection is, of course, a very important part in research. So first of all, we went in, did a really in-depth literature review. So this field of RPA, of robotic process automation, is still quite novel. So it's more or less possible there to really go in, do a systematic literature review and look at pretty much everything that's there. And from that, we selected 24 peer-reviewed research articles and conference papers. So that was our closer selection of literature that we came up with. And then to not only look at the theoretical part, but also look at the practical part of what's really happening in regard to RPA in practice, in companies, and so on. We conducted 13 expert interviews. 8 of those were with software providers. So those that really have a perspective on what are the challenges of this technology, what can it do, and what can it also not do. And then also with 5 RPA integrators. So those are the people that really have the application perspective, so to say, and can then really, give some input from that. Using all of this information that we already had at that point, we developed a model, so more so a process for our research. So what are the steps that you actually have to follow if you want to apply RPA in any sort of project? How do you actually go about selecting the correct processes before you then apply this quantifiable model that we have? So then in order to actually collect some information or some data in regard to how we can actually quantify this model, we did a big survey with 717 surveys being sent out, all to experts, so such software providers and integrators that I already mentioned, but also consultants, end users, and people with an academic background, such as all of you here today. And we received 134 surveys filled out back that we could then use. What did we do in this survey? We followed the analytical hierarchy process, which means that we can do a pairwise comparison of always 2 criteria. And then we want to actually figure out which ones are the most important criteria to select processes to be automated with RPA, and how can we weigh these criteria so that in the end we can receive some sort of score or quantifiable model there. So I've already been talking about criteria. What do we mean by these criteria? How can we actually really look at a process in depth and figure out whether or not there are certain criteria there that make it actually automatable using RPA? So which are the processes that we can actually apply RPA to automate them? So here you can see 8 criteria that we have taken from literature. Sorry? Okay. That we have taken from literature. And you can see here, out of those 24 papers that I mentioned, how many times, what were any of these criteria mentioned here. And we could already tell there were 2 that we had to add on top of what we had found in other existing models that tackled a similar problem, which are the digital data input and the structured data input. So you can see here really to receive the correct data is a very, very important pillar. But there's also one criterion, which is the number of interfaces involved. So this means how many different programs am I working with in this process that I would like to automate. And this criterion we have actually excluded from our model. It turned out to be not as important as the other 7 that you can see here. So now, Johannes, are you here?
I think that Johannes still has trouble connecting, because I heard this noise that you heard came from his connection. So I think
this is Johannes. Sorry, I'm dialed in now. Thanks, Maria, for sharing, and thanks for sorry for this troubles with presenting. So I hope all of you can hear me. As next, I'll present you the core of our paper, actually, which is a 3-step approach to identify and select suitable RPA process candidates. And at the heart of this 3 steps approach, it's a mathematical model which enables to objectively quantify process candidates and their suitability for being automated with RPA. So what we propose is a 3-step approach, actually, starting with target definition, second, process identification and prioritization, which has the 3 steps: process identification, data collection, process prioritization. And third is process selection based on the suitability values that the model provides. First of all, target definition is very important. On the one hand, it serves as the baseline for project success and project evaluation. So you, of course, need to know what you want to achieve with a certain automation with RPA in order to be able to judge if it was successful and if you could achieve the targets. Based on the literature review and the conducted case studies, we found that among all personal savings, it's very important as objective for RPA, followed by improvements in quality of outputs. As RPA operates more or less error-free, you can guarantee by automating a process with RPA that the outcome also should be free of errors. Other objectives can be an increase in availability, capacities, as well as performing of time-critical tasks. For example, in finance and auditing functions, oftentimes a high time pressure at month's end, where RPA can help to reduce and increase the available capacity or improving of compliance. And for this first step target definition, it's also important to have a look onto strategic decisions and the strategic objectives of the company at all, as well as on an operational level, to see if it makes sense to use RPA or to rather use another technology, mainly heavyweight IT, in order to automate the process. At the core of the approach number 2 is process identification. First, a process pre-selection is required in order to know which processes could potentially be automated. This can be done on the one hand traditionally via workshops, for example, or, and there are also interesting papers available on this, via using robotic process mining, process or task mining technologies in order to see, based on log data, which data can be automated or which process can be automated with RPA. Moreover, the process identification is the baseline for our model, followed by data collection, which means collection of data points for each process that should be assessed based on the prioritization model. And based on those collected data points, then the mathematical model comes into play, which I'll introduce you in the next slides in detail to see and prioritize potential RPA process candidates based on their suitability. This model also includes an economic assessment, as criteria such as volume, standardization, or maturity are included. And for example, of course, high volume processes account for higher savings potential. A high degree of standardization in terms of rule-based nature reduces the implementation costs, and a high maturity of processes or system reduces, for example, the operational costs. And based on the outputs of the prioritization model, then step 3, process selection follows, which is then the selection of the most promising process candidates that should be automated with RPA. In the next slide, I want to introduce you into our mathematical model that we propose to objectively assess which process is best suited for an automation with RPA. What we do here is we introduce a suitability value that you can see in the middle, which is the product, the sum over all eigenvectors, Wi in terms of relative importance of each of the 7 criteria that we have identified, and a fitness value ranging between 0 and 1 for all the 7 input factors that I'll introduce to you right away, to then assess which processes are best suited for an automation. For that, we decompose processes into sub-processes and sub-processes into a number of activities, which we then take into account for our model. Starting with the first and most important criteria, standardization. we define standardization as a process that follow a predefined structure, can be decomposed into sub-processes without misinterpretation, and for which all decisions rely on clearly defined rules with no ambiguities. As you can see on the slides, we introduce a mathematical formulation for standardization, and we look at each activity within a sub-process and assess whether this activity is following clear defined rules or not. This is based on a binary 0-1 logic. Moreover, we only include sub-processes into our model where all activities follow clearly defined rules, meaning if a sub-process within a process does not follow clearly defined rules, then the suitability of the overall process is somewhat lower. Moreover, here we also introduce a weighting factor because even so, for example, two sub-processes of a process do not follow clearly defined rules, but overall the third sub-process follows clearly defined rule and, for example, takes 9/10 of the overall execution time, then of course the suitability in terms of standardization for this process is high. Standardization is followed by a high volume of processes, which we define as total execution time of a process in terms of time required for the performance of a process and the frequency of repetitions. For volume,
I think we dropped off at volume.
Yeah, did we lose Johannes? Okay.
I think so. Yeah.
No problem there. I will take over maybe until he comes back.
Please, yes.
That the connection is not lasting from Germany all the way to. So sorry for that.
Cool.
Yeah,
that's okay.
Yeah. We finished off we stopped at volume there, which is the second most criterion that we have identified, and that is, of course, the product of time and the frequency of repetitions, as you can see in this formula. Third most important that you can see here is the manual effort that goes into this process execution. So we define manual effort as the extent to which activities have not yet been automated. So this is really the degree of how many sub-processes here or steps in this process are still executed in a manual way and which ones are automated, so that then in the end we can say how high is the potential to actually automate more out of this process. We will continue the input factors. As you know, there's 7 in total, with number 4, which is the maturity. Maturity we define as the stability of a process in the involved systems with low vulnerability to changes and updates. So that means really for how long did this process remain the same, so that it is not subject to frequent changes and updates, which would then of course result in this automation process to also having to be changed, which is something that you don't want. You want the process to be very stable so that it can be automated and that you can then retrieve the benefits from that over a long period of time. Fifth one, and I have already previously pointed this one out, is the digital data input. We define digital data input as the degree to which the data are available in a non-analog digital form. So of course, I said in the beginning, RPA is, so to say, a digital worker, and that means that all data and everything that is a part of this process has to be there in a digital format so that you can then also be able to automate this using software and nothing that is there in analog form, such as paper, for example. Criterion number 6 is the input data quality. We define the quality of input data as the share of activities with sufficient data quality from the total number of activities within a process. That again sounds a little bit more complicated than it is, because that really means that we need quantifiable, trackable data in the right quality, so that this data that comes in is not completely messy or random, so that it's not able to be readable by a machine, by a computer, by a software. So it has to have a quality that you can then actually use for automation. And last but not least, the failure rate also goes in as an important criterion. So we define that as the degree to which a process variant is prone to errors. So that means that if you actually execute the process and you want to automate it, it has to be possible that this process also goes through without failing in between, because then you would have to account for this exception from the usual automation, so to say. Based upon these 7 criterions that we have now been talking about, you can see here the results from the survey, where we actually then derived these weights for the selection criteria that we have previously mentioned. So these 7 that you see here on the right-hand side add up to a total factor weight of 1, of course, including the rounding of these. And this follows the survey procedure that I have explained in the beginning, where we follow this analytical hierarchy process to always compare to and then figure out which ones are the most important ones. And you can see here, as I have previously mentioned, that the high degree of standardization is the most important one, followed by all the other ones. To base this up, we also did a statistical analysis to really be sure that these weights that we have gotten there are statistically significant, and we did a pair t-test here. You can see the results in this table, but we will not go so much into detail. And the result of this statistical analysis is that standardization is significantly the most important one at a 1% confidence level here. And it is followed by the other ones: high volume, maturity, manual effort, and the digital and structured data input in the end. So now you have really already learned a lot about our model. And then finally, what we did and what we would like to point out here, because it's also very important, is that we really applied this model to a real life use case to actually be able to see whether or not our model holds and whether it works successfully. So what we did is that we went into a management accounting department of a big international technology company. We looked at a selection of processes. Those are the ones that you can see here in this graph. We collected all of the data points for all of these criteria that we have previously mentioned. And as Johannes explained, a process is not just simply a process, but it consists of a huge number of small sub-processes of individual activities that all influence this one process. And we collected data on 102 sub-processes and 792 activities, which is really a lot. We quantified all of that, and using these factor weights that you saw previously, we calculated a score for each one of these processes. And here in the graph on the right-hand side, you can see that we identified 5 processes that have a score of above 0.8 roughly, that also turned out in that real application in the company that they could be automated using RPA. The ones that were below roughly that threshold of 0.8 are the ones that are marked here in light blue. And those 4 were not suitable to be automated with RPA for different reasons that they scored low on either of these 7 criteria that we have previously identified there. So to sum that all up, in the end, we can say that the model that we have worked on confirms actually whether or not a process is automatable with RPA. We were able to really come up with a quantifiable model there, and that is very, very good, not only for research, but of course also for actual usage, because that could really serve as an objective basis to making decisions for decision makers in companies, managers, and so on, that actually have to figure out, is something automatable using RPA or not? And that of course also has a financial impact, as you may imagine. It's usually a topic with automation that you can look deeper into. Is that really worth it also to automate that or not? And here this model, since it's so quantifiable, has a huge impact. Finally, maybe 2 points that are also a little bit cumbersome here. I mentioned all these data points that we had to collect. Of course, data collection is cumbersome, time consuming. You know that. So that's why we brought up some other technologies briefly in the beginning. For example, process mining. Process mining could be used very nicely together with RPA in the future to actually detect and get more data on such processes, and then be able to know whether or not the process is automatable using RPA. And then finally, I mentioned that we found a threshold of 0.8 roughly for that use case that we looked at in the one company. And it may be a good first indicator that the threshold for this model may be at a 0.8, so that you say also roughly 80-20 that works to be able to automate such processes. But of course, you can always just start from the top using the best process and then going down from there. But there could be further research in this area to see how actually, certain technologies work together. So I would like to thank you all for your attention. And apologies again for the little technical difficulties. I think we got through that nicely. We're looking forward to being in touch with you, and of course are open for any questions.
Maria, thank you very much. It was also very impressive how you took over and managed to present the session throughout. I'm just now checking for questions, but perhaps for the first question I had on my mind myself, I saw that all of the metrics, all of the factors that you included were really process-centric. Can you imagine that in the decision-making process of which ones to automate with RPA, that there will be additional factors that organizations have to take into account other than the process factors themselves?
Yes, that's a very interesting question, because between the moment that we have handed in the paper and now, we have already expanded our research a little bit into that area to look at actually the reason why companies would want to automate. Are they just looking for cost savings, or could there also be other aspects such as quality improvement, or providing services in times where there's no one available to execute that process actually? And if you actually differentiate the model based on such other criteria, such as quality and so on, you are able to actually show that there are also other influences to that model, just like you said. So yeah, there's definitely room to expand the research there. And it's also an interesting question. How can you actually measure such things as a company wants to automate because of quality improvement, for example?
Right.
And yeah, we're already looking into that, how we can do that, and to also apply our model to that.
Very nice also that you share what you're already working on next. I have not seen yet other questions coming up. There was another.
We have a raised hand from someone, if you'd like to.
Oh, we do. Plina, sorry, I missed that, Plina. And I know you get angry with me if I miss you, so go on.
Not giving you any chance to do that. So I just like to continue with Hayo's question and ask to what extent your metrics can support a return on investment calculation.
Maria, can you try to keep it within a minute, because then we have to switch.
I will do that. Yes, we have started to look into that in the research in the meantime that I have just mentioned. And actually, when we differentiate based on these other reasons why you would automate, we are able to quantify those in an economic way, that being personnel savings, cost savings, time savings, quality, and so on. So these metrics we can quantify economically, and then we can actually look at, so to say, a matrix. So 2 dimensions. We have the score that fits, and do we have the economic value that also fits? And then if we have both of these criteria, we, so to say, add 1 dimension to what you heard now, and then we're able to make, another more in-depth decision on that.
Thanks.
Perfect. Thank you very much. It is time now to switch. Thanks again for the speakers, and we will now move over to the next presenter, Diana Sola. Diana, when you're ready.
Yes, please. Thank you. I will share my screen. 1 moment, please. Good. So I think you should see my screen now.
We are.
Great. Okay, then hello everyone. Well, welcome also from my side. My name is Diana and I'm a PhD student at SAP and the University of Mannheim. Yeah, I'm very happy to present you our work, which is about a rule-based recommendation approach for business process modeling. So let's start with the motivation. So as most of you probably know, business process modeling is a time-consuming task that requires substantial expertise. The process models have to be unambiguous, they have to be consistent. So all in all, the modeling is also very error-prone. In the case of domain-specific processes, this often also involves the use of a specialized or technical vocabulary. So modeling a business process is a complex task, and we should therefore provide some support to process modelers. Of course, there exist graphical business process modeling tools, and they already offer a repository of symbols as the building blocks of the underlying modeling language, but the elements, they still have to be manually arranged and labeled. Therefore, it would be useful to have a recommendation feature that makes recommendations on how to complete a business process model under development. Yeah, in our work, we focus on activity recommendation. So we focus on recommending suitable activities to extend a business process model at a user-given position. And since the position of the activity is given, the activity recommendation problem actually breaks down to finding a suitable label for a given node. The basis for such a recommendation feature is usually a repository of completed business process models. Good, now here we have an example of a business process model that is currently developed. And the user has just added this gray colored and still unnamed activity. The task now is to recommend labels for this activity. So the system gives recommendations on how the process can be extended at this point. Yeah, for the recommendation, it is important that the system considers the current progress or context of the business process under development. Or in other words, the recommendation method should consider what has already been modeled so far. In our example, the model depicts a version of the order-to-cash process. So a context-aware recommender system suggests activities that have also been used in similar order-to-cash processes in the repository at a comparable position, like, for example, submit purchase order. Now, how do we address the activity recommendation problem? Yeah, our rule-based method works in two main phases, and before each of them, there is a pre-processing phase. The first main phase is rule learning. The input comprises the completed business process model from a repository, and as an output, we receive a set of rules with corresponding confidences. The second phase is rule application and recommendation. Here we have two inputs. First, the result of the rule learning phase, so the generated rules with the confidences. And second, the business process model under development, which is subject to the recommendation of an activity. Yeah, the result is a ranking of recommendations for an activity at a given position. Now let's have a closer look at the different phases. We start with the pre-processing phase. Yeah, as we have seen, we have this phase before each of the two main phases. In the pre-processing, we translate the given business process models into logical formulas, such that we can then learn and apply rules. So the question is, how do we translate a process model into logical formulas? For this, it is important to understand that we consider a process model as a set of related activity nodes, where the activity nodes have labels. So we have two things. We have abstract activity nodes and activity labels. And each activity node with its ID is unique, while the labels can be shared among the process models. So for example, we have this process model with the activity node N2. This node is unique and belongs to this particular process, but the label of the activity node N2 is inquiry sent, and there might be other processes with other activity nodes that have the same label. For the logical formulas, this means that we add such a formula for each activity node in the business process model. And these formulas just tell us which nodes of which processes have which labels. So for example, we have this inquiry send of N2, and yeah, this just tells us that the node N2 has the label inquiry send. Now the process model can be further characterized by the relations between activities. In the simplest implementation of our rule-based approach, these are the relations that we use. So we have a followed by relation that tells us that an activity can be followed by another activity. and we have an in-same process relation that tells us that two activities are in the same process. So for each relation between two nodes in the process model, we then add such formulas. For example, this one tells us that the node N0 is followed by the node N1, or this one tells us that the nodes N0 and N1 are in the same process. Yeah, with the followed by relation, we cannot distinguish, for example, between an AND and an OR split. But it is possible to capture the semantics of a process more precisely. And yeah, in this case, one can distinguish between these four more specific variants of the followed by relation, as for example, direct always causal. And additionally, one can also consider the concurrency between two nodes. In this presentation, we stick to the followed by relation. More details about the other relations can be found in the paper, but what you can surely already see at this point is that our method is easily extendable. Good, so this is how the preprocessing works, and we can do this with all given business process models, and the result is then that we have transformed the given business processes into a set of formulas such that we can learn and apply rules. Good, so let's go on with the rule learning phase. In this phase, we want to generate certain types of rules. Well, our goal is to predict the label of a node. So we are interested in rules where the head comprises the label of a node. Here, L and later also H, J, and K are placeholders for the label of an activity. So for example, L equals quotation send. Okay, so now we know how the head of the rules that we want to learn should look like. What about the bodies of the rule? With the rules, we want to capture regularities in the use of activities. And such regularities can be expressed by the relations between two activities. So we will make use of the relations followed by and in same process in the bodies of the rules. Yeah, in order to keep full control over the types of rules that are generated, we define this set of rule templates. The rule templates are just different combinations of relations between activities, and they capture different types of probabilistic regularity. The probability of a rule that instantiates template 2 tells us, for example, how probable it is that a certain activity with label K is followed by another activity with label L. And the probability of a one rule expresses, for example, how probable it is that if an activity with label K is used in a process, another activity in that process is L. And here we also have a concrete example, which is an instantiation of template 1. Good, the rule learning then consists of replacing H, J, K, and L in the rule templates by the possible labels from the repository and computing the corresponding confidences. Good, what about the rule confidence? Yeah, the confidence of a rule can be understood as the probability that it makes a correct prediction or recommendation within the given repository of processes. For the calculation of the confidence, I have again prepared an example here with 2 rules. And in this example, the first rule with the head submit purchase order applies 2 times in the given repository of business processes. Or in other words, in the given repository, there are 2 process models in which the activity quotation received is followed by the activity submit purchase order. The second rule with the head analyze quotation applies only once. So there's one process model in which quotation received is followed by analyze quotation. As we can see, the bodies of the rules are the same, only the heads of the 2 rules are different. And we assume here that there is no other rule with the same body. So we assume that there are only 3 models where inquiry sent, where quotation received occurs in the given processes. Then the confidence of the first rule is given by 2 divided by 3 because we divide the number of occurrences of the rule, which is 2, by the number of occurrences of the body of the rule, which is 2 plus 1, so 3. In other words, we know that the activity quotation received is used 3 times in the data set. And in 2 process models, it is followed by the activity submit purchase order. So we divide 2 by 3 to get the confidence of the rule. And accordingly, the confidence of the second rule is given by a third. Okay, now how does the application of the rules work? So here it is given a process model with a position for which we have to find suitable recommendations. And let's call this position n star. For the generation of recommendations, we now go through all the learned rules. And for each rule, we set z equal to the node for which we want to recommend a label. So in this case, n star. And then we check if the body of the rule applies in the given process. And if this is the case, then the head of the rule is a recommendation. Here again, I have prepared 2 rules as example. And now the first step is to check for both rules whether the respective body applies in the given process model under development. Now we see that the first rule applies because the unlabeled activity follows the activity quotation received, and it is in the same process with create and submit a quotation. The second rule also applies because the unlabeled activity is also in the same process with inquiry send. So both rules apply and lead to the recommendation submit purchase order. Now here I have noted the confidences of the 2 rules, and as you can see, they have 2 different confidence values. So one is 0.4 and one is 0.6. But of course, we can only assign one confidence value to the recommendation because later we want to rank the recommendations based on one confidence value. So the question is, which confidence value do we assign to the recommendation submit purchase order? Yeah, in our work, we present 2 different options for this. The first option is the max aggregation. Here we just assign the maximum of the confidence values to the recommendation. So in this case, this would be order 6. In the noisy OR aggregation, we subtract the confidence values from 1, multiply them, and then again subtract the product from 1. Yeah, this is based on the so-called noisy OR distribution, which is a simplification of the dependency relations in Bayesian networks. And in this case, this leads to a confidence of 0.76. Good, now in the end, we have a list of recommendations, each with 1 confidence value. We can sort the list of recommendations based on the confidence values and then output, for example, the top 10 recommendations. Okay, now we have seen how the method works. Now we need to think about how to evaluate activity recommendation methods if we only have a data set of complete business processes. So basically, we don't want to make a user study. Instead, we want to use a set of completed business processes for the evaluation. And therefore, we have to simulate intermediate states in the modeling process. So the basic idea for the simulation is that some activities and associated edges are removed from a given complete business process. Now for the evaluation, we have 3 different scenarios, which are given K, BFS, and Heidlas-2. And these evaluation scenarios just differ in how advanced the modeling process is. So they differ in the available context for the recommendation. Yeah, in the given K scenario, there are K consecutive nodes, and we want to generate recommendations for the node on position K plus 1. For example, in the case of K equal to 3, we would want to generate recommendations for the blue node and use the orange nodes for that. In the BFS method, we randomly select 1 node for which we want to generate recommendations. Then we use all nodes that can be reached from the start in less or the same number of steps as the randomly selected node. So if again, the blue node is the randomly chosen node for which we want to predict a label, then we would use these orange nodes for the recommendation. And the most information is given by Heidlas-2. Here we take the end node out of the process, and then we generate recommendations for a node before the end nodes, so for a second to last node, and use all other nodes for the recommendation. So in general, we see that the most information is given in the height class 2 scenario, while the least information is given in the given case scenario, and BFS just lies in between. Good, now we come to the experiments. Yeah, we made a 10-fold cross-validation. As evaluation metric, we use the hit rate, hits at 10. Hits at 10 is just the fraction of cases where the activity that was actually used in a process model is among the top 10 recommendations. So among the 10 recommendations with the highest confidence score. For the evaluation, we employed a model collection of the BPM academic initiative. The data set comprised 15,365 process models, where we only use BPMN models with 3 to 50 activities and English labels. We compared our method to 2 simpler baselines and 4 sophisticated methods, including an embedding-based one. So we have co-occur. This is a recommendation strategy that recommends activities that just co-occurred most often with the so far inserted activities of the model under development. KNN is a k-nearest neighbors-based technique. The 3 models, link context, chain context, and hybrid context, take the order of the activities in the process models into account. Here, link context is limited to activity chains of length 2. Chain context is more general and considers longer chains of activities. And hybrid context combines a contextualized version of KNN with link context. And last but not least, we have RL recommender, which embeds activities and behavioral relations into a continuous low-dimensional space. Good, and here are the results of the experiments that we conducted. In the lower part, you can see the result of our method with the different confidence aggregation methods. So we have max and noisy OR. And as we can see, our method performs very well. In particular, it is the best method except for the give one case, but the give one case is also a rather specific case since only one previous node is given for the recommendation of the next node. And whenever more information is given, our method outperforms the other methods. Good, then we already come to the conclusion. Yeah, our method is better than many other approaches. It can be extended very easily. So you can use other rule templates, you can use other relations between activities, or you can use other methods to aggregate the confidence values. Also, since it is a rule-based approach, we can easily generate explanations for the recommendation. Yeah, for the plans, as our method was inspired by rule-based knowledge graph completion methods, we would also like to apply such methods to the problem and compare it to our approach. In fact, we already did this and submitted it to the BPM workshop AI for BPM. Yeah, in future, we also want to use the semantics of the labels for the approach, so not only the relations between activities, but also their meaning. Okay, that's it. Thank you for your interest. And yeah, now I'm happy to listen to your ideas or answer your questions.
Jana, thank you very much for your very clear and also very concise presentation, which leaves us ample time for discussion.
Yes.
I see there's a question by Ralph. Ralph, do you want to formulate the question yourself? Then you can open your microphone.
Okay, so my question is, do you allow any variability when it comes to the naming of the labels? If you have a label called submit purchase order, does it have to be exactly the same, or would you consider a similar label with in fact the same meaning as being the same? And if you do so, how do you find out which labels refer to the to the same task done on the same objects?
Yeah. Okay, thank you for this question. So I think there are two sides concerning this question. So first of all, we have the method side, and in the method, we don't do this at the moment. So we really only look at the same label. So it has to be submit purchase order. It can't be submit PO or something else. And on the evaluation side, as we do it in the method, we also evaluate it this way. So it really has to be the same label as it has been used in the process model that we evaluate. But this is exactly what we want to do in future, what I'm working currently on.
Very nice. Are you satisfied?
Thank you.
Yeah,
thank you too.
Okay, very well. We move over to Martijn Koot. Martijn, you can open your microphone.
Yeah, that's me. I hope my microphone works well because I just plugged it in, so I see
you
a
can
few
hear
nods.
you clearly.
Yeah, okay.
Yeah.
Okay, luckily. No, I was wondering, in one of your slides, I saw that you used approximately 50,000 process models to learn the recommendation approach, how to recommend. And I was wondering, assume I'm building a model myself. I don't want to have a model that everybody else uses most of the times. I want to have the best practices. I want to have I want to have a model that works properly, not what is common. So how can you improve the quality of your own recommendations by closely examining the training data set?
Yeah, so your question is how we can assure quality. Did I understand that right?
Yeah, and then you can ask, okay, what do we define by quality? But I want to have the best performing process design that is possible for my, I don't know, use case. Yeah,
okay, I see. So, well, in this case, you should hope that there were many people that designed it in the best way, whatever this means, because of course we only work on, evidence. So if this has been used quite often, then you will get a correct recommendation, I would say. But here you have to be, hope in the knowledge of the others, I would say. So we don't have a quality assurance thing in the method. Maybe this would be a nice idea, to combine it with some quality methods.
Yeah, I think that's the point, that Martijn, perhaps there are other considerations to be taken into account when you're modeling, but Diana, you're right. You need data, or you need some prescriptions to include that. But I think it's an interesting thought. I also saw Sasha has a question.
Thank you, Hayo, and thank you, Diana. Very nice, very clear presentation.
Thank you.
Very quick question. So I was just curious how you designed the rule templates.
Mm-hmm. Yeah, that's an interesting question. So, basically we had this different definitions of the relations, and then we tried out different things, and it was from the beginning, it was very clear that we have to combine this co-occurrence patterns with the structural patterns. So which order of the activities are important. So this was a point that was also already clear from previous work, and then we just tried to combine it, and this was actually the way how we came to this rule templates. So we started, in fact, with the relations and then just combined different things. I hope this answers your question. Thank you.
It does? Okay, very nice. Diana, I remember there was also work by Agnes Koschmider, and I also saw that in your work you referred to one of her papers. And one of the, so she worked on activity recommendations as well, but she took a rather different approach.
Yes.
She was looking at the properties of the modelers themselves, and tried to reason from similarities between modelers, how similar modelers, for example, working in the same domain, could benefit from modeling decisions by other modelers. So can you perhaps reflect a little bit on the differences of these approaches and the pros and cons, perhaps also the opportunity to combine things here?
Yeah, great. Good question. So yeah, as you already mentioned, she had this approach where she looked at similar users. And I think this is probably inspired by recommender systems from other domains, like e-commerce or something else. It's a really nice idea. But I think the biggest problem, or why I didn't follow such an approach or thought more about this, was that you never really have the data. So it's a really big problem to get process models and information about the users who created these process models. It's so in the moment we don't really have big data sets, and I really needed a big data set for the rule learning. I mean, you need it for every machine learning technique that you want to try out. So I think this is the point where we said, okay, we can't do it like this, or we can't really follow that.
Yeah, I see it, but I also understand that if people would now, after your presentation, come to you and give you the data, you would probably
this would be cool. Yeah,
okay,
would
good.
Be great.
That's a call for everyone then. All right. Thanks again. Also, thanks for all the interesting questions raised.
Thank you very much.
Let's move to the last presenter in this session. We do that a little bit early, so that we are also all in time for the awards ceremony, which immediately follows this session. So let's move to Bernhard Schäfer, the next presenter. And while Bernhard is preparing to share his screen, I also want to mention that the paper itself is really worth looking into. I did it myself, and I saw that it has all kinds of nice visualizations, but I'm sure we will see many of them in the presentation. Bernhard, when you're ready, go ahead.
Yeah, okay. Thank you very much for the plug to the paper. Yeah, of course, always happy for people to check it out. So yeah, my name is Bernhard. I'm a PhD student at SAP Intelligent Robotic Process Automation, like the presenter Diana before, and also a PhD student at the University of Mannheim. And happy to present our work, Sketch to BPMN, automatic recognition of hand-drawn BPMN models. So let's dive in. So regarding motivation, the first version of a process model is often created using pen and paper or whiteboard, and then subsequent versions are created with specialized process modeling tools. Now, this switching from analog to digital creates quite some friction because the user needs to manually replicate the sketch process in a modeling tool, and this involves considerable time and effort. And you can see this manual process here in the bottom, where you have maybe took an image of a whiteboard or pen and paper drawing, and then somebody replicates this in a modeling tool, and you get typically standard BPMN XML. And so what we propose is we want to automate this step, and our method is called Sketch to BPMN, which takes as input such an image and then automatically transforms this into an XML file. Now, if we truly want to automate this task, there are a large number of recognition challenges that we have to overcome. First, we have a real-world example here to showcase some of them. The first thing here is that there's a customer pool here on top, and it has only been partially drawn, but we still want to recognize it. So this is something we have to face with. Then the second thing here is we have visible shapes from the back of the paper that we don't want to recognize. And you also see this on whiteboards when they haven't been properly cleaned from maybe a previous session, and you still have some things visible that you don't want to recognize. Then there's also interrupted lines here of a lane because it collided with this textual label. Or you have lines that cross each other, which make especially error recognition very challenging. And you also see frequently things that have been crossed out, which are also challenging because you don't want to recognize them. And so what we propose is the sketch to BPMN method, and it consists of 3 main steps. So given this image, we first detect shapes and edges, and this produces a set of candidates. And then we have a structure recognition step that produces a model that we can then in the output generation step transform into this BPMN XML file. And I will now walk you through the different steps. So the first step here, the shape and edge detection, this is based on Arrow RCNN, which is a previous work of ours. And this is state-of-the-art in several hand-drawn flowchart data sets. And you can see an example of such a flowchart on the right. And it's built in turn on faster RCNN, which is a popular deep learning approach for object detection. And, oh, sorry, can you still see my presentation? Okay. It's in turn built on a set on faster RCNN, and the objects are detected as bounding boxes with a predicted category and a likelihood. And you can see this on the right, where you have bounding boxes for example, arrows, and then text, data elements, etc. And then what's kind of special about Arrow RCNN is that we have a dedicated arrow network that predicts the head and tail key points of each edge. And we use this later for structure recognition. And so in this work, we basically trained our RCNN to detect 21 different BPMN shape and 3 edge classes. And we performed 2 key adaptations to improve first on the key point detection, and then also extended the data augmentation method so that it works better with images, for example, taken with a smartphone. And here you can see the shape and edge detection results for an actual image after training our improved model. And the candidate shape and edge bounding boxes have been detected here. And also edges have these additional predicted head and tail key points, same as in the flow charts. So you can see this here, where an arrow has here a tail key point and also a predicted head key point. And we can use this later to reason what shapes this arrow connects. Now, the second step of our approach is BPMN structure recognition. And it consists of 2 main tasks. First, we want to remove unlikely shape and edge candidates. And then, as mentioned, we want to use those arrow key points to determine the source and target shape of each edge. So basically the shapes that are connected by this arrow. And regarding the first task on the right, you can see an example where our model predicted 2 duplicate shapes with different classes. And we identify these duplicates by measuring the bounding box overlap between all the candidates. And in case of a conflict, we keep simply the candidate with the higher probability. And then regarding the second aspect here, we have an edge post-processing mechanism to figure out the structure. And in the original Arrow RCNN work, there was a simple heuristic where the source and target shape of each edge are simply defined as the shapes closest to the respective tail and head key points. And in our work, we improved over this baseline by applying more fine-grained rules that also take into account the modeling language itself. And here I want to show just one example of what such a rule looks like. So on the right, you have a message flow with a tail key point denoted here as a blue circle. And it's in fact closest to the bottom pool. So with the standard Arrow RCNN post-processing, the edge would be incorrectly linked to the bottom pool as shown in the small visualization. And but we actually know that such a message flow is not valid in BPMN, and also what's important, we consider it very unlikely that somebody would model such an arrow, and therefore we have a rule in place that detects these scenarios and then would correctly assign a message flow to the pool on top, because it's the object with that is closest after the first, next to the first pool. Yeah, and we have further more of such rules in place that help us basically in this post-processing procedure. And then in the last output generation step, we use the final shapes and edges of the structure recognition to create a process model in BPMN XML format. So this image here shows the real recognized model, and it has been converted to an image here and then overlaid over the hand-drawn sketch. And in this example, all the shapes and edges have been correctly recognized. And in the future, our approach could be complemented with, for example, an automated arrow layouting method, which most modeling tools already have built in. Okay, the next topic is kind of one of the key drivers of our work, which was the collection and annotation of our own hand-drawn BPMN data set, which we refer to as HD BPMN. So regarding the collection, we collected 500 true hand-drawn diagrams from 107 university students. And each image in the data set corresponds to a solution submitted to a modeling task in a graded exercise sheet or exam. And then we needed to annotate the data set, and to this end, we created our own image annotation tool that we also made public, and that is based on an open source modeling tool. And so what we did is we basically uploaded each image here, and then in this tool, we modeled the entire BPMN process on top of the drawing. And then we can download the BPMN XML, and using this XML file, we can actually extract the bounding box of each shape and edge and use that to train and test our model. So overall, the data set has more than 25,000 annotated shapes and edges. So you can imagine that this was quite an undertaking in terms of annotation effort. And the data set is publicly available on GitHub. So feel free to check it out. Now, to give you an impression of the large diversity, we collected some examples for 14 out of the 23 shape categories in the data set. And you can see already that shapes can be drawn very differently. For example, there are various ways how to draw an envelope for a message event, or also how to draw the clock in a timer event. So if you focus on these timer event examples, you can see various ways on how to draw such a clock. And it's important to note that we intentionally did not restrict the students in how they draw and hand in their solutions. So as a result, the data set has also a large variety in terms of the pen and paper that was used, and also the camera or scanner that they used to capture a photo of their drawing. And this in turn results in a large spectrum from maybe low resolution blurry shapes, such as the message event here, and then all the way to very clean instances of shapes here with high resolution. Next, I will now discuss our evaluation setup. So we evaluated our method on the data set that we collected, so HD BPMN. And to this end, we created a random split over the participants to make sure that the diagrams of a student only appear in either training, validation, or test set. This is common practice in diagram recognition because this way we can measure to what extent our model generalizes to previously unseen drawing and writing styles. And with respect to the metrics, we also used standard diagram recognition metrics. So for shapes, we consider a predicted shape as true positive if the predicted class is correct, and if also the bounding box overlap with the ground truth shape is larger than 50%. And this is typically assessed with an intersection over union measure. And then for edges, we use the same criteria, but we in addition require that the correct source and target shapes have been identified. Okay, so now before we get to the overall results, I want to introduce some of the configurations that we tested. First, we trained the Arrow RCNN approach from our original paper. And in the original work, we used image augmentation methods that are targeted at small scale data sets of black and white diagrams. And then next, we also trained two configurations to basically quantify our improvements over this baseline. First, we, as mentioned, developed an extended augmentation approach where we added augmentation methods that simulate properties of camera-based images. So during training, for example, we randomly blur the image or maybe change the brightness, change contrast to really synthetically increase the size of our data set and make it more robust to all these different ways on how such a diagram can be digitalized. And then second aspect we tested is our rule-based BPMN specific edge post-processing procedure that we already introduced. So here are the overall results. As you can see, the original Arrow RCNN approach already performs quite well and is able to recognize more than 93% of the shapes and 85% of the edges. And if we now apply our extended augmentations, we see a significant uplift in both shape and edge performance. And then last, our edge post-processing mechanism further improves the edge F1 score by nearly 2%. So in summary, our sketch to BPMN approach, which is represented here as the last row, correctly recognizes more than 95% of all shapes and close to 92% of all edges in this challenging data set that we collected. And here you can now see the detailed results for each shape class, which also showcases basically how many different classes we distinguish. And here the count columns, which counts how many times this class appears in the test set. They also indicate that the dataset has a large class imbalance because, of course, a task is used far more frequently than maybe some exotic event. And as expected, we see that the count is somewhat correlated with the F1 score because our model cannot generalize if it has seen a class just a dozen times. And this is basically what we expect from a deep learning model. And if we just look at here, for example, the shapes that occur more than 100 times, we see that the F1 score is always higher than 95, which also suggests that if we collect more data from these rare classes, we would also see uplift here. And we also did an error analysis and observed that our model struggles to distinguish the different message and timer events. And here is again this part of the figure that I showed before. And I think that's quite understandable, because when you look at the examples for the timer events, for example, the only difference is the additional circle in the middle. And so even as human, this is very challenging. So for example, here you have to really zoom in to see that this has actually 3 circles, whereas the example left to it has 2 circles and should be a start timer event instead of an intermediate timer event. And similarly for message events, the difference between the shape symbols is very small. It's typically just a line more, a circle more or less, or maybe a thick circle, or then filled out envelope, or a standard envelope. Finally, we also measured the results per edge class, and you can see that sequence flows are easier to recognize than message flows and data associations. And to some extent, this is again due to the class imbalance, because we have many more sequence flows in the data set. But this also has to do with the notation and modeling patterns. So a sequence flow, the notation is a solid line, and that's yeah, should be quite straightforward to recognize compared to message flow and data associations, where we have dashed and dotted lines, and where we also have more variety in terms of how people actually draw them. And then the second aspect that we listed here is that sequence flows tend to be straight arrows. I mean, or let's say many of them are straight arrows between nearby shapes. And message flow and data associations, they can be very long range with direction changes, which makes recognition more challenging. And this can also be explained by the fact that the data perspective elements are often drawn last. And there's one example here to visualize this point. So in this example here from the data set, it appears as if the main process was modeled first. So this message event and sequence flows, and you can see they're connected by straight arrows. And then probably afterwards, the data objects have been added and then connected to the shapes that were already in place. And this results in more complex arrows that frequently cross each other, which is challenging from a recognition perspective. Okay, so this brings us to the conclusion of our presentation. So we proposed the sketch to BPMN approach, an approach that automatically recognizes hand-drawn BPMN models from images. And we also introduced the HD BPMN dataset, which is a publicly available dataset of manually annotated hand-drawn BPMN models, and could also be used to research various other aspects with respect to maybe a process of process modeling. And then we also did an evaluation and showed that with those 2 key adaptations, we can outperform the Arrow RCNN, our previous method for flowchart recognition, which is state-of-the-art in this domain. And last, regarding future work, we plan to recognize the intended instead of the actually drawn model to already fix certain drawing errors, because we see that often, for example, maybe user would draw an intermediate event as a start event, but from context, it's clear what the user actually intended to do. So we could fix such instances already from a user perspective. I guess this would be more pleasant. And then we also want to integrate an off-the-shelf handwriting recognition solution, and then assign each word to the corresponding shape and edge, so that we actually figure out the label of each shape and edge. And in the example on the right, I think you can see that for words that are in an activity, this is mostly trivial to figure out that it basically labels the enclosing activity, but it this whole task is more complex when you have words that label edges or maybe something like data elements. And so even as a human, you need maybe a certain amount of time to figure out that complete here labels the sequence flow and not maybe the data association on its right, or maybe the data store and so on. So this is something that we're working on at the moment. Okay, so finally, feel free to check out our actual demo. So we have a website where you can upload your own image and then download the generated BPMN XML file. And yeah, by uploading those images, you can also help us to further expand our data set, yeah, which would help us to train even better models. And yeah, thank you for listening, and happy to answer questions.
Bernard, thank you very much. That was a very clear presentation, and as I hoped, it was also very nicely visually supported by all kinds of examples. Beyond the nice ideas, it also gave me inspiration for the wallpaper in my office. So if your tool could also generate these kind of pictures, I would be very grateful for that feature. We now turn to the more serious questions. And I saw that there was a question by Martijn Koot, and this is also, I think, about a sort of a future application or extension of your feature. Martijn, would you care to formulate your question yourself? If not, I can do that. Martijn was wondering about the use case.
Yeah, I pressed the wrong button, but I can ask.
Okay, go ahead.
No, thanks for the nice presentation. I also enjoyed the visualizations, but my question was already a little bit answered during during your future research points, because I was wondering, yeah, when I see all your sketches coming along, they are way better than the sketches that I produce myself. They are full of errors and yeah, it's one big mess. And often there are, yeah, invisibilities included in them as well, because yeah, it's a sketch. So what to do with when the initial sketch that you insert into the system is full of invisibilities and cannot be reconstructed in a feasible model by itself? How to address that?
Yeah. So yeah, I think there are several aspects to that. And yeah, I agree that sketches can be even more messy than what I've shown, although I've also, I mean, the data set itself has a large tail of sometimes very difficult images where you maybe have an entire diagram that has been with strike through, and then somebody, you know, started again, or you really, so I didn't show all the very messy parts, but I think that, the more messy it becomes, of course, the worse the recognition results, but I think especially for the shapes, it will typically do a good job. And then the question is, basically, at what point is the effort in creating this model from hand again to digitalize is more effort than to use the produced output? And yeah, but I would say in summary, you typically get at least some results, and that should, especially once we also integrate the handwriting, should be then less effort to basically add the rest manually than to start from scratch. And yeah, the question is, can we, how do we encourage people to draw more accurately? And it's hard to say. I mean, if you use the tool, then after a while you will probably figure out that it makes sense to draw a bit more neatly. But then also, if we had a larger data set, the model would also become better and better over time. I hope that answers your question.
Yeah, thank you very much. Maybe you and Diana should work together, that when the system cannot find out itself what the designer meant to model, maybe then Diana should recommend what the user should do.
Yeah, great suggestion. Yeah. Makes sense.
Yeah, thanks for the answer.
All right. So there's another question by Armin. Armin, please go ahead.
Thanks, Hayo, and thanks, Bernhard, for this nice presentation and nice paper. I was thinking if this work can be extended to list the syntax and semantic error, we can correct the students' submissions automatically and get rid of many corrections. One particular question, if one element cannot be recognized, how the model react? For example, we see a lot of, instead of a start timer event, a student just draw the clock without the outer circle. So how does your tool recognize that?
Yeah, yeah, great question. I mean, actually, what we presented here was also with that scenario in mind. And I think you can partially solve this in deep learning with the way how you annotate the images. And we actually, if you want to, so our aim was to recognize the model as is with all its errors so that you can then afterwards, you know, actually you could still manually fix many of them because often they're basically where a student maybe drew an intermediate event with just one circle, although the notation is 2 circles. And of course we could fix that, because if we realize it has an in and outgoing sequence flow, then by definition it should be an intermediate event. And so I think this capability is kind of built in now. But I could also think that in the future we could have 2 different annotations per diagram, maybe one that is more like what was drawn and the other is already contains fixes in terms of what the user actually intended, but there are a lot of subtleties here that we would have to consider.
Thank you, and nice work. Congratulations.
Thank you for your contribution, Amin. We have a question from Indonesia, Mahendra. Please go ahead.
Thank you. But actually, my question is quite related to the first speaker. So also with the previous one, I'm imagining that this will very much depend on the quality of the input itself. So have you considered of having a minimum, some kind of requirement for the input itself?
I mean, we have thought of it, but I mean, from a practical standpoint, I mean, I'm a PhD student at SAP Robotic Process Automation, and if we want to put this into a product, of course, we have to give out some guidelines in terms of how they should be drawn. And I think, yeah, I think this is kind of, we would have to collect the data set, but before that, do user research and maybe how do users typically model, and then figure out, okay, what can we actually still cover and where are the boundaries, and then collect the data set that represents that. And then also related to the question before, of course, if we have a repository of business processes or an RPA of maybe workflows or bots, we can also think about linking what we have here recognized to the actual tasks in the repository. And this would also allow us to fix some errors there.
Okay, thank you.
All right. I know that there are more questions, but I also promised to end the session early, so I will stick to that promise. I hope that the people who still have questions will reach out to you, Bernhard. I want to thank you and also the other presenters, Diana, Maria, for their contributions. I think it was a great session, fantastic work by all of you. I wish you good luck with the follow-up to these presentations, and I also hope that everybody will enjoy the remainder of CAiSE, and I hope to see all of you during the ORAT session that will start at 3 o'clock. So thanks again.